Sounds good. Hi, everyone. So we're going to talk today about some work that we've been doing for a few years with many of you, AGI at Cisco. Some of it will be applied. As we get started, I want to make sure that Oz is going to help me present some of this. Oz, are you there?
Yes.
Excellent. And you guys can see my screen, I hope?
Yes.
Can you see my screen?
Yeah.
Everybody? Yeah, okay. Okay, so when I say AGI in the wild, I literally mean I was in South Africa installing systems last year, which was great. I think I gave this update last year. We have systems that we are focused on open conservation, trying to apply more intelligence, video cameras, infrared sensors, a lot of other sensors, trying to prevent poaching of elephants and pangolins and rhinos and all of that. So that's actually out there working. This is kind of a high-level slide. I'm not going to dive into that too much, but we were doing some video analytics. The smart city work that we're doing right now, is it big enough for you guys, or do I need to go full screen? We'll just leave it. I guess you guys can see the screen fine. Yeah. Go ahead.
It's large enough, I think.
Sorry, Patrick, what did you say?
No, I think it's large enough. It's fun.
Okay, good. Thank you. So the smart city work that we started last year, Tony Lofthouse, Patrick was very much involved with this. The basic idea here was we had a video analytics that, using our own multimodal deep learning models. We wanted to add NARS to that, and the task at hand that we applied was, can the system automatically calibrate itself, learn what its field of view is, learn where the roads are, the sidewalks, all of that, and we wrote a paper on that. So Patrick was the primary author, so there's a paper out on that. This is an ongoing project right now, and it's actually in Australia. It's growing, and we're hoping to kind of re-engage. And my plan, so my personal plan is, and I do have approval, is to open source much of the video analytics that we're doing, open source the framework, open source how we're interfacing to NARS and all of that, so that we can get more of a ecosystem, more research interest. That would also, help us to kind of further develop social good applications. But in Australia, for example, what they're doing is they have complex intersection environments where you have trains, you have bicycles, you have pedestrians, as well as the vehicles. So there's a lot of safety concerns, and we want to apply just more adaptive, intelligent analytics that could start to understand when potentially you have an emergence of dangerous conditions. So it's a great use of reasoning in that space. One thing that we do, significant research with universities. This is some examples of what we're doing. Ben Gertzel, Pei Wang, Kristen, and hopefully more. I also have some things that are more focused on just the deep learning side, security related, and data fusion, multimodal scene understanding. It's quite interesting to see how you can build these models now with deep learning, where you can, if it's multimodal, which means like you have sound and video, for example, you can generate one modality from the other. And the nice thing about one thing I've been pushing multimodal deep learning for quite some time is that you have the ability to, for one modality to implicitly label the other. So you don't have to worry about, they're unsupervised techniques in a sense, but not really, because one modality, so you have correlation and temporal correlation occurring across them. So that's a little bit of background on some of the things we've been doing. Some of the papers that we've done, some great work by Alexei Popov and Ben's team on re-identification across cameras when you're doing that kind of tracking. And there's more online. If you look online, and like I said, expect a lot more open source coming from us in this space. This is the paper I mentioned that Patrick was the primary author, but some good results there, and ongoing project there. And I know Patrick has done some great work with OpenNARS for applications, which we will be incorporating and updating that software probably in the coming weeks, to incorporate that. So as I get into like what we're currently doing, that's kind of more historical. I mean, and it is ongoing, but our current focus kind of evolved from that. I just want to give a little bit of about some of the biases, I guess, that we have, where we're coming from, so you understand. I built one of the first commercial semantic networks at a company, unfortunately, called Metadata. They tried to actually protect that back in the 1980s, but that really impacted me about focusing, about how do you represent knowledge, what is knowledge, and so even though I'm very interested in reasoning and other sorts of graph processing, and Korsivsky has a huge influence on me. So you're going to see that in what we're talking about here. Keep that in mind. Also, I like basically applying AI and these academic principles into the biggest real-world systems that I can. So I have like 6 billion chips in the world that have been serialized and have my security technology on there. I have a lot of technology deployed everywhere from TV to mobile devices. So I like to kind of get my tech out there because I feel it's a great way to learn from just, actually, yeah, so it's one thing to basically have an AI that could maybe, identify one object with reasoning. Can you identify it when you have a cluster of 1,000 or 2,000 objects that you got to figure out in real time? It's a very good learning opportunity for me and that's why impact is kind of a big deal, what we're going to talk about. A lot of bias, I have to say, OpenCog, OpenNARS, ERA. I really think those are huge parts of the solution. I don't see them as, and I don't want to make anyone angry, but I think that I see tons of synergies in lots of the components. I think everybody with the AIKR principle would agree. Cognitive synergy conceptually is excellent. I think that we're actually starting to see that in some of what we're doing. So this is some of the stuff, some of the background of what we're getting into. And for lack of a better name, the thing we're going to talk about where we're kind of getting some new results, kind of combining OpenNARS and ERA, we're calling it, excuse me, DFRE, Meta Model Deep Fusion Reasoning Engine. It's just a historical thing. It's not a real name. We're going to rename that. It's just internal, but DFRE is the name of it. So we have a meta model that incorporates this idea of how do you represent knowledge, right? So we'll get into that in a second. So last year, I presented this slide, and it kind of, at that point, I was still kind of more on the neuro-symbolic approach. How do you combine machine learning, deep learning, which has a lot of great things about it, nice pattern recognition capabilities, obviously a lot of problems as well. It's not going to get you to AGI. Symbolic AI, how do you mix it? So it was a kind of a neuro-symbolic architecture, which we're still doing, with a middle layer, which Peter Gardefors kind of hypothesized, and I felt was quite important as well, which was some mechanism, kind of a metric space, where you have you can go from discrete values in the knowledge graph. Red is apples are red, and red. Last time I saw red was episodic memory. There was blood, or whatever that is. To going to a is sort of an analogical with a metric space, right? Where it's like, how red is it, right? Or how do these shapes evolve and that kind of stuff. And so we started to kind of come up with the concept of, or implement this geometric conceptual space and various ideas. So one of the things how this has evolved as we apply this to networking and other, more challenging problems is maintaining the structure of knowledge is crucial, right? And so what is knowledge? We're writing a paper that is just being approved right now, but we're going to cover some of the concepts here. A few of the things really that Korsivsky talked about, back in the 30s are quite crucial in our view. And I think more people are kind of raising this again, which is, the importance of distinction, individuation. This is not that. To me, to us, the framework of knowledge basically is anti-symmetric relations. So how does that work? So our meta model basically is very rigorous about these anti-symmetric relations and how you deal with that. You have levels of abstraction, which I think are crucial as well, which we've implemented. Korsivsky talked about that. He has a structural differential in his Science and Sanity book that you can, kind of see what he did there. Ours is a little bit different. And then also similarity, right? So then you have the symmetric relation. So how do you, at a high level, what we're saying is you have intention, extension, levels of abstraction, and you have to maintain the structure of knowledge, right? If you have any process that works on your net general knowledge base that is not aware of all these different things and doesn't have a way of really keeping them straight, then what we found is that you get what we call knowledge scrambling instead of building knowledge. But knowledge scrambling can be quite good. If you need creativity, there's a place for that. But there's a key place for just maintaining structure. Where this really comes from is quite interesting. It was some research. Basically, right now, when you think about intelligence, you obviously think about neuronal capabilities, neurons, and modeling those things. But a lot of the work that we're doing here basically goes even more primitive intelligence, right? So if you have any kind of cell, the cytoplasm, it exhibits tropic responses, right? Even plants, they like heliotropic, they'll go towards the light, geotropic, they go towards, they understand where gravity is, and they work in that sense. Cells exhibit the same thing. How does that work? I mean, they're exhibiting intelligence. They don't even have any, obviously they don't have neurons, they're single-celled organisms. So how does that work? And it turns out that a lot of what is happening could, the boundary between the animate and the inanimate, life and non-life, seems to be kind of quite an interesting place where you get some intelligent behaviors. And that's kind of what they call electrocolloidal or colloidal chemistry. Wolfgang Pauli kind of hypothesized that. He actually wrote a book on this, and he said this is kind of where a lot of the intelligence is happening. And interestingly, in colloidal chemistry, that maintains this knowledge structure. It'll have levels of abstraction. It has the knowledge. It has this individuation, symmetric, anti-symmetric. That'll even happen without a cell. It'll happen in just colloids. But anyways, that's a bit of background on what's happening there. Now, how would we apply this? These are some of the, kind of one summary slide. I don't know, Oz, you want to jump in and say something about this one?
Well, actually, this shows the capabilities that we can use with the FRE. We have we collect basically the sub-symbolic data from different sources. Could be retail, smart cities, or networking. And currently, we're actually working on networking and time series analysis with this architecture. And the set of services provides an agent the capability to ingest various data sources with different data modalities. This could be structured text. This could be programs, audio, and any sort of data. And the symbolic data is constructed. And the agent constantly creates the abstraction of this physical world at different layers. And by using expert knowledge, reasons on this data and constantly creates the knowledge graph. So we keep everything in the system as a graph, not only knowledge, but also the reasoning steps and the results as well.
So it might be worth saying a word here on tools. I didn't quite, highlight that in the prior slide that, we're leveraging, we're not trying to reinvent the wheel. If we have AGI blocks, which we leverage, we'll use those. But also there are some other major blocks that kind of stand out here. The graphs, for example, like the graph, what we're finding that the highest performance graph database out there from all the testing that we could do, it's in memory, so it's hyper fast and it's open source. It's the Redis, basically Redis has grown into like an ecosystem. I don't think everyone's even aware of it. You think of it as a tag value database, but it's so much more than that. It does every kind of pub sub graph database. It has time series specialization support. It has AI built in for TensorFlow, PyTorch. It's just a fantastic platform for anyone that actually wants to build real working applied AGI. It's it's fantastic. So we use that quite a bit. But also, since we're doing a lot of graph analysis, I would probably give a shout out to Cytoscape as well, for the visualization from the bioinformatics and genomics communities that have been the guys doing the most work hardcore on large graphs, so Cytoscape is out there, open source, it's great. And probably one last shout out to NetworkX, which is kind of our internal, we use a lot of that for a lot of the internal graph processing that we do, which is not bad. There's a Python version of that you might want to look at if you want to get into this. So we mentioned some of the data sources. We can also do a lot of out of band, because we have this meta model, you could pretty much put everything into it, whether it's video or audio or, anything, so we have a lot of ability to social media data, some of the applications we're looking at, this geofence concept, right, where, you look at all of the social media and other sensor data coming from a particular area as kind of another, geo-localized source, which gives you all sorts of cool things that you could do with that. And the time series I would just mention here has kind of become our de facto conceptual space. And we can turn anything into a time series. I don't know how much, if you have any background with time series, you'll know that you can actually turn shapes into time series and vice versa. You could pretty much DNA into a time series. And one other thing I would just say, is for time series, basically Iman, who invented matrix profile, says that it's like the world-changing technology for time series, and he's kind of a modest guy. I'm going to have to say that it's a very great building block, that matrix profile. So if you have any time series or anything that you could convert into time series, highly recommend that you take a look at matrix profile. So it's, we just use all these things, and we are adding our own elements as well. Anything here, Oz, that you want to say?
Yeah, this is one of the use cases we worked on, actually. So the agent, in that use case, agent is batch processing more than 7,000 time series. So time series, as Hugo said, is became our basis data, input data, and the system actually creates symbolic information based on that, like the structural breaks, anomalies, discords, and the spikes, square waves, etc. The idea is to create a symbolic language-like representation of the time series, and then reason on that. So this time series actually was based on Yang models, which is data representation language. It was also another source of information for the agent, not only the time series itself, but also we used information coming from Yang models. Hugo will show in other slides. I think it's on slide 16.
And right now we're interfacing. So this is, you actually get about 8,000 time series from a single box in a network, for example. So we're looking at getting a processing right now. We're interfacing now about 1 million time series live for like one reasonably sized environment, right? So, and we have a way of doing that, and it's not unlike what Antonio was talking about, where you need to have a focus of attention, and that's where AGI comes in. Otherwise, the combinatorial explosion issues are really not manageable. Go for it, Oz.
Yeah, as Hugo said, the main one of the main communication between the services and the agent is provided by Redis. So Redis time series holds the data. For example, a Redis AI holds a trained MLDL models, and you can use the GPU to quickly forecast what's going to happen, for example, for a time series, and also Redis itself to communication among agents, because one of the demo is going to be about collaborative agents collaborating on a task. So
I'm guessing we're not going to have time for that one. We'll do one demo maybe. Yeah, but yep. Okay. One other shout out here, just because I see it, is that the Grafana is fantastic for time series. And what we've added to it is that you can have an AGI generated dashboards, which I know doesn't sound like a big deal. So what if AGI can generate dashboards? But if you're dynamically looking at, millions or, large amount of data, and then based on some semantic principle or semantic quality, you can say, okay, here are some dynamically generated dashboards. I mean, it's a world changer, really. So I have never seen anybody do anything like that, but it's very, very useful. Yeah, so here, yeah, go ahead.
Here, as I mentioned before, for example, agent works on the Yang model names and creates an extra information on top of time series, and this gives us a chance to analyze time series in groups, for example. After detecting events across all the time series, we can say focus on event 1, and then as you can see, we have the structures preserved between the time series. So this allows us also to study the causality among the time series.
And what's really cool is that we can not only dynamically generate dashboards, but we dynamically visualize the evolution of the knowledge graph as the system is learning, which is very useful, actually. It turns out that you think it's just like, okay, what does this mean? But it actually tells you areas that you require more structure, or that require some kind of connectivity or some creativity to, so we have now, in a sense, an objective function about trying to build, knowledge structures that have certain qualities where, the visualization just helps you kind of understand what you have. This one is just, it's an initial attempt at some graph summarization. I think that Ben is really the master at different ways of doing this, but there's some new things out there that we found that are very useful. KGIST is a good grammar-based, graph summarization and compression. And I would also basically say VOG is kind of old, the vocabulary base, but there's a lot of interest right now because the graph, but this is really driven more by people that actually have large knowledge graphs or large graphs, which is going to be more the bioinformatics guys at this point. But there's a lot of good work there that probably translates into AGI as well. So we're going to talk about one use case. Really, this is a bit of just a scaled out version of what Antonio already showed you. So what we're going to show here is that we built a system that the initial task was, okay, in retail, you want to have a camera, just point it anywhere, automatically learn where the shelves are, where the products are, train itself on the products, do rectification of the image, and then just start giving you inventory, right? Fully automatic. We built that. That was in November. Right after we built that, then we got the direction to say, well, no, you probably want to focus on networking. So this never really went anywhere. It might become something later on, but at the moment, we'll show you briefly what it does. But the interesting thing here is that we learned a few things when we went from applying NARS, say where you have rules that give you one object, so suddenly you have thousands of objects, and we'll show you some how that worked. And that changed the dynamic a lot, and it really kind of forced us to have focus of attention, a mechanism for maybe like a semantic decomposition of the problem in some way that you can handle these issues. So all of that kind of built up to where we are now with the DFRE meta model. Do you want to say anything on this slide, Boz?
Yeah. So like the row bounding boxes, when you create a world based on just boxes, and then convert this into some semantic, visual semantic representation of the world, like containment information, which box is on the left of what other box, etc. You end up with thousands of premises. When we convert this to narcisse, for example, you end up in thousands of premises, but which required, as Hugo said, the employment of focus of attention mechanism.
And something like a semantic decomposition of the problem, right? Which just kind of came out of the DFRE meta model.
Yep, exactly.
So go ahead if you want to say some more dive into the
with a very simple ontology of just 4 statement rules, and we were able to process the knowledge graph and achieve very close to 100% success rate in categorizing what's a product, what's a shelf, what is not either of them.
I'm going to say that we were 100%. I mean, it was just most runs would be 100%, but there's some non-determinism, that I believe it was in NARS, but we never actually verified that, and that caused it to occasionally go slightly less than 100%. But you're being very tough on the system there, but okay. That's all right.
Okay, 100% success rate. Yeah. The good thing about one thing also that we should mention, that the nature of the symbolic data processing and the seeing the world in boxes in this case introduces noise, like counter evidence. So NARS was great to deal with that, taken into the noise consideration and the counter evidences into contradiction, and given the focus of attention, a time to process all the information, we were able to get the 100% success rate, identifying what's a shelf, what's a product, and what's not either of them.
So how much time do we have left? I think we're at the 12:30 point. Should we wrap it up, or do we have a few more minutes? We could show a little bit more.
No, you can actually show a little bit more. The max you can add to it is 30 minutes.
All right, but so is that 5 more minutes?
No, I said the max that you can add to it is 30 minutes.
Oh, wow. Okay. All right, so this is good. No. Well, let me bring up, let me see if I could, so I'm not a Zoom expert here, but I want to bring up a video to show you guys. How does that work? Stop the share, I guess. Okay. And then share. Now, this is going to be a very boring video, but it's interesting for discussion because to me, something startling happened here. So I'm just going to play this. So it's a video of this retail system, and initially it's going to be kind of operating on the, and I'll jump around on this, but it should start showing something here in a second. So first it did the rectification. It was the camera angle was at an angle. Here's kind of all the raw output from some of the, and you can see there's a lot of false positives, happening here. And then we ran the, this is about 10 times slower. We have a real-time translator that goes from the NARS log file into a graph and bidirectional. So we typically interface external systems with this bidirectional mechanism that allows us to have a graph representation, in both ways. This one we slowed it down just for visualization here, but it runs quite fast. But as it runs, you can see it's not really making any mistakes, right? And it'll do the whole image. That's fine. And to be honest, we didn't do anything to train specifically for this. I mean, the rectification logic was parameter free. We tried it on a lot of cases. There was nothing specific about this. And to get 100% was a bit unusual. So what we decided to do was say, okay, well, let's give it a different image that's a little bit unexpected. Like that, here this was built on the concept of shelves. So I wanted to say, okay, let's take an image where it's all blurry, plus there are no shelves to see what it does. And it got like, I think it was about 90% accuracy, where it wasn't completely blurry. So that to me is a different regime of operation, right? If you're doing MLDL, you know that you have to, to get these kinds of results, you're very lucky, and you have to, and you have to be very concerned about that your new data set matches the prior distribution, right? That what you're doing now is very, very similar to what it was trained on. Here we purposely said, okay, we're not going to even do anything. And it just started, and we saw that it was really working quite well. And we gave it a few more examples where a different one here, okay? We just random images. Can you rectify the image? Can you find the products, et cetera? And it did a really good job on multiple cases. And I was quite excited about this, because I know it doesn't seem like a very big deal or a big problem. I mean, again, this runs in real time, so it normally would take a few seconds to give the actual results. But what was really fascinating about it was that it works so much better. I built a lot of machine learning, deep learning systems, and it's just, you never get to 100%. You have to work super hard to get into the 90s. And then if you give it something that's way outside of the training data set, it's not going to work at all. And here, it's like we couldn't really break it. and it's not, and I admit, what's the big deal? Rectangles, right? But it's an indication that we have something useful. So I'm going to show you, maybe you could say something. I'm going to bring up the cumulative learning demo.
Yeah. Maybe I can tell about the semantic decomposition. So one way to tell the agent to do it, maybe based on color. So, okay, focus on the regions based on, let's say, where you see the red pixels more, just like human being, or the contrast. Here in this example, the examples Hugo showed, the system was focusing on the creating decomposition of the problem as the largest non-empty rectangle. Okay, find me the most crowded area and then work on that. Once you're done, move to the second most crowded one, and so on and so forth. With such a simple logic, we were able to deal with the combinatorial explosion actually, and give the reasoner time to think about it and reason in a detailed way.
So the next example, when we were still IoT last year, we won't be able to talk too much about like where Cisco really is using this, which is going to be for networking, security, the core business. That's where it's going. Obviously, it's going to be, we're already getting some pretty amazing results. When you do have the meta model, right? Because now it's like the first real formal. I mean, what we see, it just appears to be a great empirically proven approach to representing knowledge, and you use this as your basis while you have all these different learning engines running. what we noticed is that for free, you basically get cumulative learning, right? Because they're all basing, typically you have the same seed ontology, if you will, or you have the same, the ontology doesn't have to be just in RZs, it could be pretty much in any language, or it could be an actual standard ontology. There's a lot of ways of getting the ontologies in there. We have our own DFRE script as well. But if you have an ecosystem of these things, basically, we're going to show some cumulative learning that just comes out of the box, which is also very cool. Hopefully, a lot of this will be open sourced soon, because again, I think that we have approval for the IoT-related smart city stuff to become more of an ecosystem that we just support in the background as we focus on networking. But maybe Oz, if you want to talk about this, you can go get into that. The use case.
Yeah. In this scenario, there is a hit and run situation. So each camera actually, or each agent has its own camera. It's better to say each camera has its own agent. So one agent witnesses a hit and run situation, sees the accident, and then another car runs away, and then raises an alert. So in this use case, the focus of attention mechanism actually triggers the other possible agents that might see a clue about the running car. So the focus of attention here knows the location of all the other cameras, and actually one of them sees another car.
Your audio is kind of fading there. At least it was for me. I don't know if it was for everybody else. But one of the key advantages of NARS in this case, by the way, is the adherence to AIKR, right? Which means that, so right now, Cisco has adopted the video analytics that we built. They're on camera, right? And you need to have the NARS run on camera, which it's very, very efficient. So the AIKR really is making a big difference on these kinds of applications. Here's the overall architecture. Oz, if you want to say a word there.
Yeah, so this use case actually is a simulation of collaborative learning. So each agent has might have its own ontology, but also they together construct a knowledge graph cumulatively about a car running away, causing an accident. Yeah.
So at the time that we built this, we didn't have the real-time ability to visualize the evolution of the knowledge graph, but it would be very cool. Oz, I know it's not our focus right now, but hopefully this kind of work that we've done in IoT will continue on. I think there's a ton of potential, right now, so many applications. But what the new framework we have applied to this problem retroactively would be really significant. You want to say something here? I'm going to bring up the video too.
Okay, so well, actually, this summarizes what we use for visualization. So the Redis is the main database. We're
losing your audio. So basically, in the demo we have these 7 agents, and it's kind of a basic. Again, it's not very exciting. It's like the last demo. We could pretty soon actually we could show some videos of this stuff working live in Australia and other places, but that'll be maybe next time if you guys decide to call us back. I'm going to stop sharing this and. That's strange. It's not showing up as a sharing option, unfortunately. Give me one. Okay, it's there. But you can't see. You don't see anything on the screen, correct?
Correct.
All right. I'm gonna try one last thing. There seems to be some issue here. Okay, sorry guys, it's not coming up, but for whatever reason, it's not that application is not showing. The video won't show. It's not showing up. But it's in essence what you were going to see was just this implementation of all these agents coming, basically doing cumulative learning. right? So I think that's in large part what we wanted to show you. And this is the tip of the iceberg. You know, when we're able to have more discussions into what's really happening with the time series, the combination of having the static information from, you know, that you learn from all these different ontologies, and Oz, when he got his degree with Pei, was focusing on I think WordNet and ConceptNet. I mean, so we're ingesting all that stuff out of the box, and there's other ontologies. We have a lady at Cisco and a team that have been working 20 years to build a Cisco knowledge graph. That's in here, obviously now. So things are happening pretty quickly, and we're looking at a lot of other ways of bootstrapping the initial knowledge, and also, you know, with the input being time series, the sky's the limit. I mean, it's just such a generic way of inputting knowledge about the real world in real time that I think it's quite promising what we're seeing here. But thank you for your time. I mean, and for all the researchers that we're working with currently, you know, you're making this possible. We're very thankful for all the support and ideas that you have. And like I said, we're pushing to do more open source, and I think we're going to be publishing some papers on this, and hopefully we can jointly do extend some of these ideas as well. But with that, I'd just like to wrap it up. Thank you.
All right, thank you very much for this talk. Let me see. Does anybody have questions?
I have a question.
Hey, Patrick, long time no see.
I have a question about the visual attention mechanism you use. Because it seems like you're processing only small parts of the image, right? In the product identification, it's only
yes.
So, what is the guiding principle here? Which what priority are to look at?
Right. So basically, you know, we have the DFRE meta model where you have all the rectangles go inside of there, and then we have a small amount of logic that basically gives you spatial semantics, right? And so for the spatial semantics, you have the basic things you would imagine, you know, containment relationships. You have you know, several other very basic things, and we're able to basically that was a very easy problem of using kind of what I would call like a semantic decomposition. Although it wasn't a clean partition because there was some overlap in the partitions, but that was okay. It didn't matter. It gave us enough of a decomposition that we were able to completely address combinatorial explosion issues. And right now, if we had 10,000 rectangles, it would be no problem. So yeah, and that's an area right now that we're thinking more about, like different, you know, we'd like to have more generic decomposition mechanisms, and that's where we're finding some pretty useful things happening in the graph space. You know, to find like if you look at graph compression or graph summarization, ways of finding fundamental structures that are in the graph to describe the graph, those are likely ways of decomposing the problem as well. And because we have the layers of abstraction, that also helps you. The layers of abstraction give you, you know, a nice structure of knowledge that you can use to decompose problems. And it is fairly compatible with NAR's intention extension, but not 100%. So, but it's very synergistic. And one area that I would say that NAR's looks very, very promising to us is when you have, say, you have an existing meta model of graph, very complex, and you the problem requires that you connect two distant pieces of knowledge. Right? How do you do that? There's evolutionary techniques. There's other techniques, plausible chains of inference that connect ideas that you couldn't see before. But yeah. And by the way, thank you so much for all the support, Patrick. You know, we're hoping to bring you into the Australian project.
Yeah. And I find this very interesting. Also, a visual attention approach is a good candidate to be generalized in a general vision system, which can also work for other domains.
It's completely general. The basic spatial semantics could operate on anything. So it could be. There's a lot of other domains, and currently the design that we had was trying to actually represent images as time series. So to all the shapes, you know, the edges, all that kind of stuff would be a time series, so that we can apply our time series of, you know, but because we had a very limited time, we just ended up using a like a YOLO, the latest version of YOLO, and we just basically made it so the confidence was like 0. So it gave you every possible rectangle, right? So you had thousands of rectangles, but with reasoning, you know, and the spatial semantics information, you were able to get good results.
Well, that's interesting.
We could, yeah, I think the non-parameterized image rectification may also be interesting for some of the work that you're doing in robotics as well. You know, there was, yeah, there's something to talk about later, maybe.
Maybe I'll let someone else ask a question now.
Yes, I have a question, Hugo.
Yes. Hi, Antonio.
Hi, Hugo. Thank you for your talk. And there are many contact points between your vision system and my proposal of focus of attention. However, I think that you consider rectangles. So in any case, it should be useful to take into account even the three-dimensional aspects of an object, for example. No? The fact that if you consider, instead of considering rectangles, you consider the full 3D aspects, and more the fact, for example, that a system, just like a robot, may navigate through the scene. You have a more rich vision system.
Yes.
This is my view.
No. So we agree with that, and that's why we like the meta model. You know, that we didn't dive into too much. But what the meta model allows you to do is to have n-dimensional representations and connections in the graph space. And so what you can do is you can say, okay, so now give me a focus of attention that incorporates this particular attribute, this particular dimension, you know, and so we call this, internally, this is kind of the L2 more abstract space, where you can kind of have many overlapping, you know, abstractions and hierarchies, you know, so 3D, 4D, you know, it all fits with what we're doing, definitely. And to be honest, right now, like I said, we're really focused more on multidimensional processing of non-visual data. I feel kind of sad that we got to this point that we couldn't use it for anything, which is why I'm trying to get it to be open source. So hopefully we can do much more. But really, the work that we've done with the meta model and the graph space and all that, I think that could be quite useful for a lot of projects, actually. Very high performance, by the way. We're seeing, you know, the Redis time series. I don't know how many millions of data points per second. It's huge. I mean, very, very fast.
Well, in our use cases, we had 1.2 million, but I think it can go up more than that.
Yeah, and you were using the batching, right? Like processing 10,000 time series at a time, something like that.
Yeah, it was like 25 million points, actually, 25 million data as a batch process. But we can.
I would just recommend against, you know, trying to build like new fundamental components like that if you have, you know, if you don't have a real very solid need for it. And the way that Redis is built, if you want to customize it, they have a Lua interface that you could build into the engine itself. So it's very hard for me to justify doing, you know, not using Redis right now for a lot of things.
Okay.
Okay.
Thank you.